Lecture 6, Operations Scheduling, Part 3, and this is the last part of this chapter. In this part, we will have the assembly line balancing problem, and this is known as a classic industrial engineering problem. So here we have an end product, let's say our product and item, and each item of the end product will include n tasks. So in order to complete one item of the end product, we need to do all those n tasks. Okay, so we have n tasks which they should be done in order to complete each item, I mean one item of the end product. And the time of task I, we know this, and it's showed here by ti. And here our goal is this: we want to actually group the tasks in order to assign each group to a workstation. So we will have a number of workstations. So at first we need to know how many workstations we need to have in order to produce the end product, and how to assign the tasks to each workstation. So because of that, here we are talking about the grouping of the task, because each group will be assigned to one workstation. So the criteria here, the criteria of obtaining the number of workstations and grouping the tasks in order to assign the workstations is having a cycle time. So if we have a desired rate, I mean, if a desired rate has been obtained in advance, so we need to do the line balancing in order to, I mean, have that defined cycle time. But if we don't, then we will do the line balance in order to minimize the cycle time. And and also another criteria here that we want to have is having somehow a balance between the workstations. I mean, the total time, I mean, the total processing time in workstations should be as much as possible close together. Okay, so this is why we do have the balancing word here. Okay, so in grouping and assigning the tasks to workstations, we may have some constraints. For example, precedence constraints. So we should consider precedence in assigning the tasks to workstations. And also we may have this constraint that some tasks may cannot be performed at the same workstation. Okay, so now let's show the time of the tasks by t. So t1, t2 up to tn will be the task times of n tasks. So if we add up these times, we'll have the t as the total work content associated with the production of an item. Okay, now if we do have a cycle time, so what's the definition of cycle time? Cycle time is the time that every the cycle time we will produce one end item, one product. For example, if the cycle time is 5 minutes, this means that every 5 minutes we will produce one product. Okay, so now if we divide t by c, the total time by the c cycle time, and the bracket here means rounding up this number, so we will always round up the number to the next larger integer. Okay, so then n here will be the number of workstations, so n is always greater than or equal to t divided by c. Okay, let's have an example here. Green Grasses plant manager just received marketing's latest forecasts for fertilizer spreader sales for the next year. So she wants its production line to be designed to make 2,400 spreaders per week. Okay, and the plant will operate 40 hours per week. So as you see here, this will be our throughput rate, right? Per week actually here. So the throughput rate per week should be 2,400 items. And we know that we operate 40 hours per week. So if we want to have the throughput rate per hour, then we can divide um, the throughput per week divided by the number of hours per week, which is 40 here, so it will be 60. So this means that the throughput rate here should be 60 spreaders per hour. Okay, now the cycle time here will be 1 divided by the throughput rate. Yeah, anytime that we have a production rate or the throughput rate, then 1 over the throughput rate will be the cycle time. So if, for example, we have 1 over 2,400, that cycle time will be in terms of week, right? But if we want to have in terms of hour, so the cycle time will be 1 over 60, right? So 1 over 60, which becomes 1 over 60 will be our cycle time in hour, but since we know that each hour includes 60 minutes, then 1 minute or 60 seconds will be our cycle time here. Okay. Now let's continue the example, and we know that these work elements, or let's say steps, should be done in order to produce one item of the fertilizer spreader. Okay, so we do have the tasks or work elements here, and also this is the description of each work element, and we do have the processing times in seconds. So we do have here, and also we do have the predecessor relationship between the work elements. So, for example, here I see uh, the B work element B has a prerequisite which is A. So A should be completed in order to start work element B. Okay, so yeah, the total processing time here is 244 seconds. So as you see here, we do have the total processing time, which is 244. That's our T. And also we do have the cycle time, which is 60 seconds, right? So if we divide T by C, 244 divided by 60, it will be 4.07. We always round it up, so it will be 5. So 5 will be our minimum number of work stations. This is also called the theoretical minimum number of stations. Okay. Now, in order to continue solving this problem, we need to draw a precedence diagram. So yeah, I mean the precedence relationships can be shown in a diagram. It's better in order to do analysis. So we draw a precedence diagram. So each node here is one of our work elements, and the arrows here or the arcs actually are showing the precedence relationship. So A is a prerequisite for B, and then B is a prerequisite for D, and also E, and then H has two prerequisites, D and E, and yeah, as you see here. And the numbers that we have for each node is the processing time. Okay, so yeah, in order to start uh, uh, assembly line balancing analysis, we need to draw a precedence diagram like this. Okay. Now, in order to group the tasks or work elements and then assign them to a work station, we will consider these uh, criteria. The number of workstations required is minimized. So we have a minimum number of workstations, right? It's N, T divided by C. So that's the minimum, and we want to keep it as if it's possible or if we need to increase the number of workstations, we should minimize the number of workstations. And the precedence and also cycle time requirements are not violated. Okay, and also the work content for each station is equal. So, but or nearly so, but less than the cycle time for the line. Yeah, we will try to make a balance between the workstations in terms of the work content. So the total time of the workstation should be so close together as much as possible, and the total time of each workstation should be less than the cycle time in order to not violate the cycle time. Okay. So for our example, the minimum number of workstations is 5 and the cycle time is 60, right? So now we want to see how can we group the tasks and assign to workstations in order to meet the precedence requirement, the precedence relationship requirements, and also the cycle time. So the first one, A, as you see here, has 40 seconds. So we can't uh, include any other work element here, because after A we can include B or C. But as you see here, B has 30 seconds, C has 50 seconds. So if we add one of these two elements in this group, then the total time will be higher than the cycle time, right? So because of that we can. So just one will be, just A will be one group. So one group will be just A. After A, so we can go for the rest of the work elements. Again, with the same reason, C will be again just in a group, so we can't include any other work element in the workstation with C because of the processing times. So the third group can be, after doing A and C, we can go for B, F, and G, right? But as you see here, B and F, if we group these two in one workstation, the total time becomes 55. So it's so close to 60, so it's good. So these two will be the third group, and then D and G again, we will have the total processing of 55, and at the end E, H, and I. So 26, 36, 44 will be the total time of this workstation. So here we have 40, 50, 55, 55, and 44. Yeah, as you see here, they are not exactly the same, but this is the best actually option that we can have here. So because of that, we can say this solution is somehow the optimal solution. Okay. So now we can calculate some performance measures here. The first one is the efficiency. Efficiency is sum of over the processing times divided by n times c. So as you remember, n is the number of stations and c is the cycle time. Okay, so here the total time, as you remember, is 244. We have 5 workstations and the cycle time is 60, so 5 times 60, it will be 81.3%. So this means that the efficiency on our assembly line is 81.3%. So this means that since we have 5 stations and the cycle time is 60, so in total we have 5 times 60, which is 300 seconds as the total work content in the 5 stations, right? But the total work content that we do have here is 244 seconds. So because of that, the efficiency of the assembly line is 81.3%. And the balance delay here is called is calculated by this 100% minus efficiency, it will be 18.7%. And idle idle time here is NC minus sum over T would be 56 seconds. So this means that in our assembly line, in any cycle, we have 56 seconds as the idle time. Okay. Let's have another example here. A company setting up an assembly line to produce 192 units per 8-hour shift. So as you see here, we need to produce 192 units per 8-hour shift. So by these two data, we can easily calculate the cycle time. And here we do have the work elements for each item of the product. So we have these work elements. We do have the processing time of each work element in seconds, and also we do have the precedence relationship between the work elements. And the total work content here for each item of the end product is 720 seconds. Okay. Okay, now we first calculate the cycle time. Cycle time is 1 over the throughput rate, so it will be 1 over 192, and this will be in terms of day. So yeah, I mean, the cycle time is 0.00520 day per unit. If we want to have this in terms of seconds, so we can easily convert this, which is in day, to be in seconds, right? So as you see here, the cycle time becomes 150 seconds per unit. This means that we need to produce 1 unit every 150 seconds in order to be able to meet the demand requirement. Okay, and we do have the sum of total work for each unit of the product, the end item, is 720 seconds, right? So now by having the T, the cycle time C, we can calculate the minimum number of workstations. So N becomes T over C, which would be 4.8, and we round it up. So the minimum number of workstations can be 5. Okay, so the next step here is drawing a precedence diagram. So we do have the relationship between the work elements, and so by having that, we can easily draw a diagram to show the precedence relationship between the work elements. Also, okay, so let's go ahead. So for the first workstation, since we're starting from the beginning, so the only option here is A, right? Yeah, it's just A, so there is no choice than A, so the choice will be A. And the work element time in second is 40 seconds, so the cumulative time for this workstations will be 40 as well. And since the cycle time is 150, so there is 110 seconds left in this workstation. So now we assume that we have done the work element A. Now let's see what other elements can be added to this workstation. So after completing A, we can go for B and G, right? As you see here. But G has 120 seconds as its processing time, but we have just let me show with the color here. We have just 110 seconds left in this workstation, so G is it cannot be added to this workstation. So the only option now again becomes B. So we do have B here. Again, there is just one candidate, so the choice will be B, and its time is 80 seconds. So the cumulative time in seconds for this workstation becomes 120, and again 30 seconds left in this workstation. Now we are right here. We are here. We are done on B, and as you see, we can go for D, E, and F, right? And as you see here, the processing times of here we have 25, 20, and 15. All three are less than 30 seconds. So we can have all those three as candidates here. So we do have three candidates, D, E, and F, right? And so we want to choose one of these candidates. So I see here D has 25, and if we choose D, then we will have less idle time in this workstation at the end. So because of that, D is a better choice here. So we choose D, and 25. So here it becomes 145 and 5 seconds left as the idle time. So we can't add any more for on this workstation. So we are done on workstation number 1, and we go for workstation S2. Okay, so as you see here, we have scheduled a, oh sorry, we have scheduled A, B, and D on workstation number 1, right? So for workstation number 2, considering again the precedence relationship, we will see what are the candidates, and then by the same manner of workstation 1, we go for the other workstations, okay? So here we have completed the table, and we do have the solution of the assembly line balancing. So as you see here, we have assigned work elements A, B, and D to workstation S1. Then workstation 2 includes the work elements of G and E, and then workstation S3 just includes H because of its time. It's 145 seconds, just 5 seconds less than the cycle time. And then S4, we have assigned I and F to S4, and then S5 includes C and J. Okay, so yeah, we are done on this example, and this is our final solution. Okay. So as a performance measure for our assignment, we can calculate the efficiency here. The total work time divided by N times C. And let's see here, we have 96% efficiency, which is pretty good. And this means that we only have 4% as the balance delay here. So it's a pretty good solution. Okay. So now, yeah, we are done on this chapter. We will have more examples on the live session on Tuesday. So see you on Tuesday. Thank you.